Hello everyone, how are you? Okay, thank you for your comments. Well, you actually read my mind. So Paul is asking, I was thinking the deadline for the bonus portion of the assignment should be extended. Yeah, that is exactly what I wanted to do. Yeah, but I will talk about that later. But yeah, I will. You literally read my mind. Okay, so how are you, everybody? We have 40 participants. I guess a lot of people is still struggling with the assignment. So yes. So the first thing is yes. I am very happy to see that a lot of people is actually trying to get the bonus point. I think historically, not many people try that because it's quite challenging. So yes, I was thinking that it was cool to maybe give an extra date for that. So the thing is, it will be an extra day only for the bonus points, which means that if you don't want to use any late days, right? You need to submit today on the night the first part, right? I mean, everybody needs to do the first part. However, if you are trying to pursue the bonus points, yeah, you basically have one extension day. But remember that we don't count the weekend days, right? It means that you can still work for the bonus on Saturday and Sunday and even Monday, right? So basically, you have until Monday night. So yeah, I think you deserve it. A lot of people is trying to get the bonus point. So yeah, and it is challenging. I tried to answer a couple of questions about that on Piazza. Maybe maybe you have the impression that I'm not being like giving too detailed explanations. Like my explanations are not too detailed, and this is just because I don't want to give you the answer, right? I mean, the math in the end is not that hard. So for example, the math to compute the length of the virtual links, right? It's not that hard, right? So, oh, okay. Someone is asking, how do we submit the bonus? Actually, I was my intention was to discuss this with the TAs. I guess Ibo is here, probably. Ibo, are you here?
Yeah, I'm here.
Okay, so quick question, Ibo. Could they submit the bonus part also using handing? So basically, like sending two files. Is that possible?
Yeah, just have the other extra file handed in with a zip file and submit it with them together. And when we're grading, we will just modify the HTML file so we can
Okay.
run their JS file.
So we don't need to modify anything on the handling, or you need to like create another handling only for the bonus?
No, we don't need to do anything else.
Okay,
Yeah,
good, perfect. So could you please help me also, Ibo, and maybe post this on Piazza that we decided to give an extra day
yeah, okay.
for only for the bonus part, right? Only for
Yeah,
the bonus part. And of course, if someone is pretending to not sending anything on Friday and just send everything along with the bonus part on Monday, that will be wrong, right? Because in the end, we want the first part without the bonus part, without the bonus day. Okay, so again, I am trying to help you a little bit, but not too much, because otherwise I will give you the answer. Probably, I mean, after everybody gets the coding assignment, I will obviously make an extra video explaining exactly how the solution could be. Yeah, but for now, just keep working. It's not that hard. Okay. Good. So let's see. Give me a second. So I'm already sharing my screen. I'm also recording already because we had a problem last time. And by the way, the video is already there. Remember that we had the problem. I had the problem that I was not recording the first part, right? So the video is already there, and actually I modify a little bit how I was explaining in the video. I try to be more precise in terms of my explanation, depending on how, the things you ask. So if you were on the lecture, maybe that's fine, but maybe you can like check the video only for the first part. Maybe there are a couple of things that could be clear. Okay, so today we will talk about lights and shading. That's our second part, our second day, sorry, talking about lights and shading. So we have these learning goals, shading models, and lights. And we will have a couple of demos, and you will see some nice code, right? And actually, the code that you will see today will help you to solve the next coding assignment. The next coding assignment will be released on Monday and is regarding shaders. In my opinion, maybe I'm wrong, but I think in my opinion, this one, the next one, is probably the easiest of all the coding assignments. So yeah, I mean the next part will be the bonus part, right? Okay, and first I need to clarify something regarding the rasterization. I think a lot of people had this confusion of what is exactly what we are computing on the rasterization. A lot of people was asking if this part of rasterization that is basically getting these tiny squares is like, are we computing pixels or are we computing fragments, right? There's always this confusion of what is a pixel or what is the difference between pixels and fragments. And I think it's fair to have that confusion because it is confusing. So I wanted to explain this to you in a certain way. So imagine what we are doing there is the first part is basically to identify which pixels are covered by a certain triangle. And we have many triangles, right? So we have many pixels and many triangles. So imagine that you are, sorry, someone is asking, easier than the intro. Yes, I think. I think the next coding assignment is easier than the intro. Of course, the bonus part is not that easy, but I think it's easier than the intro. At least my opinion, right? Okay, again, so imagine that conceptually what we are doing in the rasterization part is like, imagine that you are like filling a table, right? In which each row is a triangle, right? So you have a lot of triangles, a lot of rows, and you have a lot of columns, and each column is a pixel, right? And you basically need to fill that table. The thing is, you don't need to fill every cell of this grid, right? Of this table, because not every triangle is basically covering all these pixels, right? Or not every pixel is basically colliding with all triangles. So the first thing that you need to do is basically first identify which cells you need to fill with information, right? That is the rasterization part, is checking for every pixel if it's basically covered by which triangles, right? So imagine that you do that. You basically identified which cells you will need to work, right? Computing values. And then you compute those values. Which values? Well, you need to, for each cell, for each portion of triangle that is actually, right, colliding with a specific pixel, you need to compute the actual coordinates of that portion of the triangle, the actual 3D coordinates of that fragment. You need to compute its interpolated values, right, using barycentric coordinates. So you need to compute the barycentric coordinates, and then using those barycentric coordinates, you can interpolate its color, its normal, its coordinates, textures, and many other stuff, right? So in the end, we call fragment, right, to all the information that is contained on each of those like theoretical cells on this table that we want to fill, right? So a fragment is basically all that information, the information from each portion of the triangle. But of course, that each fragment, it also has a relation of which pixel is its like parent or something like that, right? If I can say something like that. So yeah, so it's kind of, that's why it's maybe confusing, but I hope this explanation is better. I will probably add maybe a couple of graphics on the PDF. Okay, so we were talking about light in the past lecture, so we already discussed a little bit a couple of these slides. So we were saying that depending on the microstructure and other characteristics of the material that we want to represent, right? is the way the light is basically behaving, right, on that surface. So depending on, for example, the microstructure of the light, depending if the surface is flat or is like very rough, right, it has like hills and valleys, the light will scatter in different directions or not, right? If it's completely flat, it will look like a mirror, and basically the light will bounce on the same direction, right? So we talk about that. We discuss also that at least for a certain type of surfaces called Lambertian surfaces, and by the way, the component that we use in computer graphics to define the Lambertian surface effect basically is called diffuse. Okay, so diffuse, we always are referring to Lambertian surfaces. And so a Lambertian surface, basically what it means is that if the light is bouncing, for example, into the surface exactly on a particular angle, right, 100% of the light will be bounced, right? However, depending on the angle from which I am viewing, right, and depending on the incidence, the angle of incidence from the light, you could have like more light reflected or less light reflected, right? And this is just because the way the light is basically distributed along this surface depending on the angle, right, of the light, and obviously the angle of the normal of the surface, right? And by the way, this theory is very old. I think I don't remember exactly right now, but the person that basically discovered this, this was, I think, in the 40s or something like that. It was it was a long time ago, and basically they were analyzing how much was bouncing on a perfect sphere, right? So they were taking photographs, and again, I mean, this is way before digital photography or things like that. This was like a long time ago, and basically they were like experimenting what was happening with the light, right? What happens with the light with respect to the surface of an object. Okay, so, and we said that there are different approaches to compute the shading or compute the color of something, right? So one option is something called flat shading, in which basically you compute a color per triangle, right? So you don't even care about vertices, you don't even care about fragments too much, right? Because in the end is, okay, I don't care. I mean, you need to compute fragments, obviously, right? You need to get the fragments from the rasterizer, but you basically compute a color per triangle, right? And you just assign the same color for every fragment that is inside that triangle, right? So that is one way to render a 3D object. And this is basically the result, right? Which is obviously kind of ugly, right? This is usually not what we want, except if you're, I don't know, making a video game like Minecraft or something like that, maybe you want to achieve this effect, right? So sometimes we actually want to achieve this like low poly, right, thing, and but in that case, that will be called non-realistic rendering, right? So every time you hear that phrase, non-realistic rendering is something that is not, the intention is not mimicking the actual reality, but like just getting another cool effect, right? So this could be useful for some low poly effect. Okay, then there are other two methods to compute lighting or to compute the color. One of those is called Gouraud shading. This is basically when you compute the color on the vertex shader, right? Not on the fragment shader, but on the vertex shader. So remember, all the vertices, right, contain a lot of information, right? So you have the coordinates of the vertices, you have the color, you have normals, you have many things maybe stored in each vertex. And you have all that information on your vertex shader, right? So basically what you do here on the Gouraud shader is for every vertex, you compute everything, right? You take all that information and you compute the color, and you define the color as a varying variable inside your vertex shader, right? So remember, if you define a varying variable in the vertex shader, it means that you also need to declare that variable exactly the same on the fragment shader, and the system will basically get that variant variable from the vertex shader, and it will pass that information through all the pipeline, right? And it will interpolate its value. So once you have you open your fragment shader, that variable, right, is already interpolated for that fragment in particular, right? Remember, fragment shader runs every vertex, and sorry, vertex shader runs every vertex, and fragment shaders runs every fragment, right? So everything is parallelized. So in that case, again, you define the color for each vertex. So the color of each fragment, you don't compute the color of each fragment on the vertex shader. You basically obtain the color directly on the vertex shader as a variant variable that is already interpolated, right? So this is basically what you obtain. As you can see, for example, here is maybe more evident. Can you see my mouse, by the way? Good. So for example, my mouse is here, right? So here you can see that the color of this pixel in particular is very well defined. Also this, sorry, the pixel, not the vertex, right? So we have a vertex here. So it's very well defined. This is another, yeah, around here is another vertex. Another one is kind of here and kind of here. So basically these are the actual colors that we computed as vertices on the vertex shader. And then the values of the fragments are basically just an interpolation of those colors, right? So that is why you see this weird effect of having like the light is kind of distributed in a very weird way. And there's, in particular, there's something very very bad about this type of shading, right? The thing is, if you remember how interpolation works, yeah, bad, I said bad. There's something bad about Gouraud shading in terms of the quality of the render. If you remember how we actually compute the interpolated values, right, using, for example, barycentric coordinates, right? The value, imagine that, in this case, imagine that this is basically this specular area from our material. Specular, I mean like the part that is shining the most, right? So basically the light is basically reflecting more in this area, in this vertex right here, right? So that like specular level, right, is basically being interpolated along these fragments. So imagine that eventually the light is changing, or the object is basically changing or rotating, and now the point in which the light will shine the most is basically in the middle of the object, in the middle of the surface of the object, and is not exactly colliding with any of the vertices, right? It means that your actual computation of the light, the computation of your light at the vertex level will be way dimmer, right? Because basically the shiny part, if the shiniest part is basically in the middle of the triangle, you're not computing that shininess, right? You're computing a value that is way more dimmer, right? Because obviously the vertices are not close to that super shiny part. So then when you pass the actual value for this fragment in particular, right? This fragment will be way darker, right? Because all the vertices that are actually around that fragment, they don't have this shininess, right? They're actually very dark, right? So what happens with Gouraud shading, and I will show you a demo, right? And you will see this live. What happens with Gouraud shading is that if the light, for example, is moving, or the object is kind of like rotating or something like that, the light, the shiniest part of the light, it appears like appears and disappears and appears and disappears, right? And this is obviously very, very bad in terms of quality, right? Okay, the other way in which you can compute it is, instead of computing the color on the vertex shader, right? You get all the information on the vertex shader, again, the color of the vertices, the normals, and many other information. And you pass that information to the fragment shader, and you compute the color on the fragment shader, right? So for each fragment, you will have an interpolated version of the normals, an interpolated version of the color, and you will have the position of the light and many other stuff, and you use all that, and compute the color at the fragment level. So see how different is this, right? This example in particular, I'm using, actually you can see how the shiny part is kind of lost, right? So for example, I will try to put my mouse in the center of the shiny section, right? And as you can see, oh, sorry, I lost my mouse a little bit. So basically the shiny part is kind of like here, right? And that is basically gone, right? Because that part is not exactly colliding with a specific vertex, right? So it's basically lost. Look at the difference, right? It's huge, right? Okay. So, quick break. We have questions? Some questions about this? Remember, right now it's just like theoretically speaking, right? Oh, sorry, Ivo is sending a message. Give me a second. Okay, guys, apparently what we will do is basically we will create a new handing only for the bonus submission, right? So the due for that will be on Monday midnight, okay? Good. Yes, Ivo, so perfect. So could you post that on Piazza, please? Okay, so yeah, so Nam has questions. Yes, Nam.
Hi. So I'm wondering, if the Phong shading is actually a lot more computationally intensive than the previous shading methods, and what breakthrough did we have that the Phong shading became the state of the art, and before people didn't really use per fragment color computation.
I lost your audio a little bit, but let me see if I understand. What you're asking is which one is more expensive?
Right. I mean, I understand that the Phong shading is the most expensive one, but
yes, of course.
What was the technological, I guess, breakthrough that led to Phong shading becoming an industry standard?
Oh, quality, because Gouraud is horrible. It's almost impossible. Okay, let me tell you something. Actually, like a long time ago, the only shader was Gouraud, right? And yet, this is super expensive, right? Because instead of in order to compute the lighting, you need to take several dot products, right? So a lot of multiplications, right? In the 70s, 60s, that was like super expensive, right? So yeah, this was very expensive at the time. Like thinking that you will need to compute the lighting literally for every pixel. Well, in this case, for every fragment, right? But and in the end, fragment is almost equal to pixels. It was just huge, right? The amount of computation. So one way to solve that problem, and one way in which a long time ago people used to solve this, was to basically subdivide the mesh in many new triangles, right? So basically, if you increase the resolution of your triangles, if your mesh is now more dense, right, you have more vertices. Now is the chances of your vertices to be exactly at the same position of your shininess parts of your light, it's basically increased, right? So that was one way in which you could do that. And maybe I'm wrong, because I'm trying to tell you this like literally by memory, but as far as I remember, there was actually that was the origin of Pixar, I think. But yeah, I think what happening is that actually Pixar designed a hardware that was basically solving this shading problem just by subdividing triangles, right? And those were basically the first computers that Pixar was selling. So the origin of Pixar is literally to solve a shading problem. But don't believe me. I will investigate a little bit more about that, and to tell you exactly what was the thing. But yeah, basically, yes, phone is obviously more expensive, but Gouraud is just horrible, right? I mean, yeah. Okay. Yushin, yes, you have your.
Yeah, so I'm just kind of confused between the difference between Phong shading and Gouraud shading.
Mhm.
So the first difference is where the final color is calculated.
Yes.
And the second,
uh-huh.
yeah, the second one is how the normals are interpolated.
Okay, good question. Okay, let's see. In Gouraud shading, you compute the color using the normals. You compute the color at vertex level, right? It means that you have the normal, you have the light and everything, and you compute the color of this guy, right?
Yeah.
Then, if the color is already computed at vertex level, basically in your vertex shader, when you pass that information, you take that color as a variant variable and you pass that to the fragment shader. Basically, you don't need to interpolate the normals. So you also save computation on that. You don't need to interpolate normals. You don't need to interpolate other data because you already have the color, right? So basically, the only data that you interpolate is only the color as a variant variable, and then you get that on the fragment shader, and basically the fragment shader has already the color, right? So just paints that color that was obtained as interpolated. In Phong shading is different, right? Because you have the information of each vertex at the vertex shader, right? And you pass all the information. You don't compute the color. You pass all the information that is necessary to compute the color, which is basically the light position, the normal, right? So, for example, here, I mean, you need the normal and the light position, right? But again, you don't interpolate those values, right? You only send the color. So in this case, again, you take all the values, send all the values as variant variables, right? So you send a variant variable with normal and a variant variable with the light position and everything. Everything arrives to the fragment shader, right? Obviously, you need to interpolate more values, right? Instead of only interpolate color, you need to interpolate the position of the light. The position of the light, no, because position of the light is a uniform variable, sorry, that is obviously fixed. But you need to interpolate the normals, right? And maybe texture color or texture coordinates, many other things. So you compute the color, right, on each vertex using all those interpolated values, right?
Yeah.
Yeah.
Okay, so
it's not that we interpolated the normals differently in Phong and Gouraud. What happens is that we do need to interpolate normals in Phong. In Gouraud, you don't even need to interpolate normals, but right, what you interpolate is just the color, right?
Yeah. So you're saying like in fragment shader, right?
Yeah. I mean, you compute the color here, right? You interpolate the remember that the part of the pipeline that interpolates the values is the rasterizer, right? It's not exactly the vertex shader, right? Remember that there are a lot of stages in between the vertex shader and the fragment shader, right? But once you are on the fragment shader, the information is already interpolated. In the case of Gouraud, you get only one variable, which is the color, and it's already interpolated, right? In the case of the Phong, you need to get a lot more variables interpolated, the normal, the color, and many other stuff, and then you compute the color, the final color for each vertex inside the vertex shader. Yeah?
Okay, so basically Phong shading has more information.
Has more information, yes, and obviously needs to performs more computations, right? Because it needs to take dot products and many other stuff per fragment, right?
Yeah, I see. Yeah, thank you.
Good. Okay, so let's continue. Someone is asking what is BRDF is this thing, it has a very weird name. Bidirectional reflectance distribution function. It's just the function that defines how the light behaves or how the light bounces on a very specific material. This is very related with physics. We will not get into that direction, right? We don't need that. Computer graphics is at least this thing that we are doing in computer graphics is more like hacking the light, right? But yeah, you just need to know that thing exists. And so, for example, sometimes you actually need to get a little bit to do a little bit of research in what is actually the physics of this thing. So for example, if you want to like represent a very specific material that maybe behaves kind of weird, right, depending on the light, there are some materials which its microstructure is very complicated, and the light is behaving kind of weird. So sometimes you actually need to take a physics book, right, and like a physics-based rendering book, and investigate a little bit, okay, how is this function actually behaves, and came up with an idea on how you can kind of imitate that effect or fake that effect. Yeah, but for now, don't worry too much. Okay, so this is Phong shading, and okay, great. So basically what happens is what we usually do is we have two components. We have three components, right? In order to create this, basically the final version of an object like this, you have three components that you basically just add, right? So one is the ambient, and this is basically, imagine that you have an object, right, that is inside a room that is closed, right? And there are no windows in that room. Well, if there is no light whatsoever, it doesn't matter what is the color of that object, right? It doesn't matter if it's red, right? That object will be completely black because just there is no light, right? So imagine that you somehow open a couple of windows of that place, but it's not. But try to imagine that maybe outside is kind of like cloudy, right? So it's not like you open a window and there's like a super, right? It's like the sun is outside or something like that. So if you go outside in a very cloudy day, you will see that basically there are no shadows, right? In a very cloudy day, you see there are no shadows, right? There are almost no specular areas in objects, right? Because what is happening is basically all the light that is coming from the sun is scattered on the clouds, and in the end, the light is not coming from one source of light, one position of light, but it's basically coming from everywhere, right? This is what we kind of like today in Vancouver. Exactly, today is basically a perfect ambient light, right? So what happens with ambient light is basically is trying to mimic light that is coming from everywhere. It's just like to give like the base color from your object, right? Otherwise, so for example, look at here. You have this diffuse component, and the diffuse component is already taking into account the direction of light. Remember, the diffuse component is the one that tries to fake or mimic the behavior of Lambertian surfaces, okay? So if the light is coming from this direction, right, of course this area, right, is not seeing the light, right? So it's totally obscure, right? But this will be very unrealistic, right, in terms of creating beautiful images, right? If we see this in a video game, for example, this will look very unrealistic, right? Because in the real world, this almost never happens, right? It doesn't matter even if you are like inside your room and you open the window and maybe the window is here, you don't see black on the other side, right? Because the light is basically bouncing on the other wall from your room, and all this light that is basically bouncing is getting from everywhere. It will get you this effect, right? It will light the areas that are not exactly on the direction of the light. So basically that is ambient, right? Ambient is just faking the light that comes from everywhere. Then the diffuse part, again, is the one that basically fakes or mimics this Lambertian surface effect, right? Remember, the surface will bounce more light if that light is basically orthogonal to the surface. It will bounce less light if that light is basically almost in orthogonal direction to the normal, because basically just the light is distributed in a larger area. Then you have the specular component, which is just basically how much your material is shining or not. And this is the part that is related with the microstructure of your material. If your material is if the surface of the material, right, is super polished, right, like a mirror, you will see a reflection like this one, right? You can see that this object right here looks very shiny, looks very polished, right? If the surface is not as polished, it means that the microstructure of your material, right, is scattering the light, right? And because we'll scatter the light, basically the light will be distributed in a different way. Okay, good. So this is sorry, I need to change. Give me a second. Let me change this very quickly because this is not Phong versus Blink. This is only Phong. Okay. Okay, so this is basically the Phong model. This is what we do to compute the Phong model. And by the way, when we usually talk about like Phong or Blink or this type of shaders, we are referring to this this portion of the lighting model, right? So this formula right here, what will compute is it will compute the specular value, right, using the Phong equations, right? So we have other equations to compute the diffuse component and other equations to compute the ambient component. Okay, so only, right, in order to compute only this portion right here, only the specular component, you can use different algorithms, and this is one of those algorithms, and so it's called Phong. And so basically what happens here is, remember, the light, the amount of light it will get to your camera, right, depends on the angle from the light with respect to the normal of the surface, right? So what this math is basically doing here is, this is the light, right, the light direction, so this is the light, right? So basically this is the light vector, this is the normal vector, which is perpendicular to the surface, and you need to first compute a reflection vector, right? So the reflection vector, if you have the light is coming from this direction, the reflected vector needs to be basically symmetrical to L with respect to N, right? So basically this angle right here is exactly the same as this angle right here. So this is the formula. If you get confused on like why this formula works, I mean, I guess you probably saw this type of math already. I don't know if maybe in another course, but if you don't remember how to compute or what is the explanation of computing the reflected vector, this is very well explained on the reading material that I will recommend for you at the end of the lecture today. Okay, so you basically compute the reflected vector, and in the end, the value for this Phong component is just the dot product between that reflected vector, right, with your view, right? And it kind of makes sense, right? If I am viewing the material, if now my camera is in another position, so let me open demo. This is Phong, right? Can you see my demo? Yeah, right? Okay. So if the camera is viewing the the object from different directions, right? Or if I move, for example, look at this. If I move the light and now the reflection vector is almost the same as the camera, right? It's pretty obvious, or it should be intuitive, that basically you will receive more light reflected, right? So you will see this point like more, like shining more, right? Because you have basically more light reflected because you're exactly on the same direction of the reflected vector, right? If the light is basically coming from another place, this will be way dimmer, right? Because now it's not as, this vector is not as close to your viewing direction, right? So basically you need to compute the dot product between R and V. Yes, it means dot product, exactly. Yeah, people is asking if it's dot product. Yes, I think PowerPoint just put this dot here and it's kind of weird, but yeah, it is the dot product. So basically it's the dot product between the normal, for the reflection vector, you also need the dot product, right? So yeah, so Phong in the end will be the maximum value between 0 and this dot product, right? The dot product between the reflected vector and the view vector, right? And you need to multiply. Sorry, you need to get an exponential, right, to elevate this to the power of g, and g is a value that you. A lot of people call this value gluciness. A lot of people call it shininess, right? So this is basically a value that helps you to define the actual behavior of your light. So again, I will come again to the demo, and let me open. Actually, I can do it here. So I will open the material editor. It's here. So let's see this material right here. Okay. Let me just change the color very quickly. The purple color of our lectures. Okay, so look at this. We have different values here. One is specular level. So this is using bling, but I can change it. So let me just quickly change it to Phong, right? Okay. So we have two values: specular level, right, and gluciness. This gluciness is the G that you see on my slide, right? So this is basically G. This is what G does. So basically, let's see what these variables are doing. The specular level is basically defining how much light is reflected, right, from the material. And gluciness is defining how the light is distributed, right? So for example, this will mimic a surface that is not as polished, right? So it is reflecting a little bit of light, but also that light that is reflected is very scattered, right? So this doesn't look like polished, right? This looks like, yeah, like a plastic that is maybe not as polished. However, if you want to mimic something that is super polished, right, that its microstructure is very flat, you need to increase the amount of light that is reflected and also modify the gluciness. So now the shiny part is more concentrated, right? It means that the light is not as scattered, right? So this will look as a more shining object, right? So those are basically, this is basically how you can like play with these numbers to mimic something very realistic, right? So again, this is Phong, right? This is one model to compute lighting like this. There's and this is basically what you can have in your what you can compute, right? So basically the final color, if you are using the Phong the Phong approach, right, you basically have three components: the ambient component, the diffuse component, and the specular component. And usually we multiply those components by some values, right? These are just like multiplier values that usually can go from 0 to 1, or from 0 to a value that is actually larger than 1. Basically, this is just like they're just weights for you to play a little bit more with your algorithm to get different results. But what is happening here is just the same as this, right? It's just the final color of each pixel is just adding the ambient component plus the diffuse component plus the specular, or the color of the object with light coming from everywhere plus the color of the object with light mimicking the Lambertian surface effect, and then the color of the object with the specular level, depending on the position of the light and depending on the surface or the microsurface of your material, right? And again, these variables right here, they will only help you to just modifying the weight or each of these components, and you can just like increase the shiny part, or increase the ambient, or decrease or increase the ambient, and things like that. So how do you compute all these things? So the first one is the ambient one. The ambient is the most simple one. It's just ambient color. This is usually, it can be white. Basically, it's like the color of the light that is, again, coming from everywhere. So remember, if we are kind of mimicking this cloudy day from Vancouver, the light that is coming from the lights in Vancouver in a cloudy day is basically white, right? So this will probably will be white. And yeah, William, you have a question? Give me a second. Let me just quickly finish this. And okay, and then we have the diffuse component, right? So the diffuse component, this one is already related with the color of the material, right? You need to get the color of the material because the material could be like red or green or whatever. You also need to multiply that value times the color of the light, right? Because in the end, if you have a white object, right, but the actual light that you will compute, right, you have a spotlight, and that light is red. Of course, your object will look red, right? Because it is white, but it will be tinted as red because the light is actually it has different color, right? So if the light is totally white, it will not care, right? It will not contribute too much. But if you have light with different colors, this will care, right? And you need to multiply that times this basically by this value, right? And remember, this is basically is this the dot product between the normal vector and the light vector. So this, right, this right here. And this is because we are trying to mimic this behavior of Lambertian surfaces, right? So Lambertian surfaces will bounce more light if the light is coming on the opposite direction of the normal, right? So it will bounce more light. It will bounce less light, as in this case, for example, if the light is coming almost in orthogonal direction to the normal, right? So this is the diffuse part. And this is the specular component, right? This is the one that is basically having this this formula right here, right? So you have some you have some specular amount, right? So you're taking the maximum value between 0 and the dot product between the reflection vector and the view vector. So this is the Phong model, taking the dot product between the reflection vector and the view vector, right? You take the max value from those, either 0 or the max value from those, right? And then you take that value and get it to the power of shininess, right? And remember, shininess, sometimes we call it shininess, sometimes we call it gluciness. In 3 to the max, it's called gluciness. And remember, is this thing right here, right? This is that shininess or gluciness component, right? And again, those numbers, these numbers, for example, shininess, this number is literally defined by you. You can choose whatever value you want, and depending on how the surface looks. Okay, questions? Yes. So someone had a question. Yeah, Nam.
Hey, maybe I missed it somewhere, but are the vectors in the Phong model normalized? So they're all between 0 and 1?
Very good question.
They're all unit vectors?
Very, very, very good question. Yes, because remember, in this case, we want to measure difference between those vectors, right? So we are kind of measuring angle. So yes, all vectors need to normalize. Very good question, very relevant. Yes, they all need to be normalized. By the way, we already. What time is it right now? It's 3:48. Okay, we still have a couple of minutes, but I might extend this lecture today. If yeah, so if obviously you have another class, that's perfectly fine for me. And if you want to like leave the room when at 4 o'clock, it's perfectly fine. But I think because I still have a lot of things to do to show, and I think I will need to extend if it's not a problem for you. Could I extend? Not a problem? Yes, Paul, you have a question.
Hello.
Hello.
Could you explain why Gouraud shading is bad again? Is it because when the light hits the material, it doesn't necessarily fall on a vertex?
Okay, let me open the demo, the first demo that I want to show you, and I think you'll be convinced. The reason is because the quality is horrible, but I think like seeing the actual result, you will probably yeah. So look at this demo, right? This is a demo in which all the light is computed using the Phong approach, right? So it's basically using this logic of taking the dot product between the reflection vector and things like that, and yeah, you can basically you have the, by the way, you have the link on the presentation, so you can also open this and you have the code and you can see the code and read it, and it's very interesting. This is from a colleague from University of Toronto. This is from Alec Jacobson, a great guy. And yeah, so what is happening here is this is here the color is computed at the vertex shader, right? This is the vertex shader. It's saying here, right? So you have all the uniform variables, the varying variables, whatever, and you are computing the color in vertex shader, right? And in the fragment shader, you are only getting one variable, that is the varying variable color, color, and then your GL frag color is just getting color, right? So you basically are doing nothing on the fragment shader because everything is here, right? So look at this. Look at the specular areas on this object. Do you see that the shiny part, it seems like is appearing and then disappearing? This is because the exact point in which that surface will be like shining the most, depending if that portion of the surface is is exactly in the same position of a vertex in particular. If it's exactly on where a vertex is, right, you will get that shiny part. But if it's not exactly on the vertex, right, basically the light will be dimmer, right? So I can, for example, change this to a sphere, and you can see the effect, right? What do you think? It is horrible? Say yes if you think this is horrible. Nobody say yes. Come on. No. Okay, kinda looks bad. No, this looks super horrible. I mean, we are in computer graphics. We want to create amazing images, like astonishing art, right? Yeah, I mean, of course it is subjective, but this is horrible. But it's not only that it looks bad, right? I mean, it's not only a subjective opinion, right? It's not a personal opinion. It is incorrect, right? Because if the shiny part of your rendering depends on the actual position from the light with respect to your mesh, right? And on how your basically your mesh is by chance, right? Pointing on the exact direction of the light or not, and basically that is affecting if your object it looks shiny or not. That is fundamentally wrong, right? That is obviously wrong. So look what happens instead of computing everything on the vertex shader. Look what happens when I change this to Phong shading, right? So Phong shading is now everything will be computed on the fragment shader. So now we will have a lot less coding here and a lot more coding the fragment, right? But look at this. This is different, right? Right? Now you don't have this weird stuff, right? I mean, it seems like the sphere is not turning because it is a sphere. But let me change it to the not, and look at this. This is not only subjectively more beautiful. This is correct, right? This is a way more correct simulation, right? So yeah, so now everything is here, right? Now everything is on the fragment shader, and now you have more variables on the fragment shader because you need to get more information, right? You need to get the normals, and you need to get a lot of things. Okay, give me a second. So you're okay. Yeah, someone has a question. Remember, I'm trying to not read too much the chat because you're going super fast. So if you have a question, yeah, please raise your hand. Yes.
So I have a question about basic Phong shading.
Yes.
So when we were computing the diffuse component, so we have material color, light color, and also NL angle. Are they like element-wise multiplications of three vectors?
Oh, sorry. Your question is, how do you define the colors, the light color and ambient color and material color?
No, I'm asking like, so to compute the diffuse, so I imagine like a material color and light color are three vectors. Is that correct?
Three vector. Oh yeah. Yes, of course. Well,
So the multiplication is just like a basically element-wise
Yes.
multiplication.
Yes, yes.
Okay.
Although, give me a second. Although material color could be, I think they're vector for, because material color you can have alpha value, right?
Okay,
Remember,
I see.
you can also play with materials with transparency, right? So if you have an alpha value, it means that that part is basically, yeah, transparent, right?
Okay, and also another thing is like, so for the ambient and diffuse and specular coefficients, like K ambient
Yes.
and K diffuse and K specular. So I understand there are like uniforms that are passed into the shaders.
Yes.
So are there any rules about like setting those?
No, they're not rules. Actually, I can play with this here. So for example, here are those values. So here's key A, key D, key S. So look at what happens. So for example, I will basically, now it's 111, right? So I will decrease the one from ambient. What it will happen is it's just a weight, right? I will deem the effect of the ambient, right? So for example, this is how the render will look if you don't add the ambient, right? Because now I'm multiplying ambient by 0, right? So I guess you agree that this looks bad, right? Because, right?
Yeah,
I mean, in real life, this never happens, right? If you have your window open, it's not that the other part of your face is completely black. It's not pitch black because the light is actually bouncing on your other walls, right? So basically, yeah, this looks a bit better, but it's just a fake effect, right? We are not actually computing the light reflecting on the other side of the room or whatever that you will do on ray tracing. But this is just trying to take it as fast as possible, right? And look at what happens if I play with the multiplier from the diffuse, right? This is only getting ambient and specular, right? Only the shiny part and the ambient part, right? So again, it's just to play, right? So sometimes you actually need those to get different results. And this is the shininess, right? Or the glossiness, right? Right? So look at this. Now this looks different, right?
Okay, I see.
So this demo is really good because you basically have the code and you can play with it. And this is very relevant, and this is basically what you need to solve your coding assignment, your next coding assignment, right? Actually, yeah, I mean, here you already have a part of your coding assignment already. You can basically, yeah, here's basically a part of the solution, right? So that's why I'm saying that in general, that assignment will be not as hard, but for the bonus points, you will need to get very creative. Okay. Again, so I think I'm already on time. You know that I usually we need to get the lecture at 50 minutes. So what do you prefer? I mean, I still have 36 participants. It is okay if I just continue? I mean, everything is recorded. If it's okay if I continue, say yes if you are okay. Yeah, of course, if you have to go, it's fine. Yes, of course, I will upload it, right? So, okay, so from this point right now, everybody, if you need to leave, you can leave right now. Thanks, Nam. If you need to leave, you can leave right now. And of course, this is recorded, so I will upload, and obviously, yeah, the video will be just longer. So if you go right now, you can just watch later. Okay, good. So let's continue. Any other question regarding this? As you can see, it's actually very simple. It's not as hard, right? Okay, so someone is asking, okay, what is the diffuse responsible of? Okay, so remember that we were saying that the physics model that we are kind of we are trying to mimic is the Lambertian surface, right? Almost all surfaces from almost all materials that are like around your world, right? So if you get any object on your room, I could almost bet that 99% of all those objects have this exact behavior, right? They behave as a Lambertian surface, which means that the amount of light that is reflected from a surface depends on the direction of the light with respect to the normal. If the light is basically orthogonal to the surface, the amount of light that it will be reflected is more, right? You will reflect more photons than if the light is basically distributed in a larger area. And this is just because the area is larger, right? Well, of course, if you get like very deep in the physics of materials, there are materials that actually absorb light, right? But we are not talking about that, right? This is just a very simple fake effect that we achieve just by like quick dot products, right? But this is basically what the diffuse component is contributing, right? It's contributing to this part, right? Of the image. Is that clear? Perfect. Okay, so let's continue. Now, again, Phong model is very old. I think it's also from the 70s, from the origins from computer graphics. I was not even there. I started in computer graphics in 1998, around that, and this is way older than me. So I think also probably on the late 70s, I think there was this scientist that, I mean, he's still working, and he's a great scientist, called Jim Blin. So Jim Blin had this idea of just following the same idea from the Phong, right? But just simplify the math, okay? And so as you can see in the Phong model, right, you need to compute two dot products, right? Because you need to compute one dot product to compute the reflection vector, and then you need to compute another dot product, right? And right now with the current computers, this seems like almost stupid, right? I mean, like saving one single dot product, it seems that is nothing, right? But it was impressively expensive at that time. So, I mean, I think I read one time that one of the first chips that it was one of the first chips that could like create this type of graphics, it was $50,000. I mean, the hardware was $50,000. So it was obviously incredibly expensive, right? So saving a single dot product, it was like a huge deal, right? So Jim Blin had this idea that instead of computing the reflection vector, he said, okay, let's do something. We have the view vector and we have the light vector, right? So let's take the half vector, right? Basically the middle, right, between the view vector and the light, right? And this is this one, right? The half vector. Well, his idea is, or his discovery, or just this geometrical discovery, is that basically the angle between the half vector and the normal is almost the same as computing the angle between the reflection vector and the view. So basically what happens is you don't need to compute the reflection vector, you just compute a more simple entity, a half vector, right? Easier math. And you just take now your specular component is now the dot product between the half vector and the normal, and everything else is the same. So let me show you how it looks. So this is Blin. Yeah, this is the time in which saving a multiplication could give you a SIGGRAPH paper and probably a thesis, and you became super famous. Right now is way different, right? The amount of contributions you need to do to science right now is impressively more, is impressively harder to contribute now than in that time, right? Okay, good. So now this is the Blin model, right? So again, we have the camera, right? Depending on the camera is the angle we get, right, with respect to the light and everything. And now this is the light, right? So as you can see, it basically behaves exactly the same. If the light is not exactly, so imagine, for example, in this case, if you compute the reflected vector, right, the reflection vector will be kind of in this direction, right? So before, you would compute the difference between, or the angle between this vector right here, which is the reflection vector, and your view, right? You can imagine that. Now we will compute this angle right here. So it's not exactly the same. That's the thing. The bleen, what you obtain, right? The shape of your shiny part of your object, right? Is not exactly the same as computing with Phong as computing with bleen, but it's just way cheaper. It's very close and it's way cheaper. And bottom line, it has almost the same behavior in the sense that if the light vector, right? If the light vector is basically in a position in which its reflected vector will be exactly the same as the vector from the view. So in this case, right? If we compute the reflected vector will be in this direction, right? So now because if it's in this direction, if you compute Phong, you will get the total amount of light, right? Because that product will be 1. So now you are taking the dot product between the half vector and the normal, which is also 1, right? So basically what happens with the difference between bleen, and this is important, the difference between bleen and Phong is not when the light is on the exact same direction, sorry, when your view direction is on an exact same direction from the reflected, right? From the reflection vector. In that case, bleen and Phong will get you exactly the same value, right? So the difference is that once you basically start to move your light, right, you will typically get a little bit more light on the Phong model than with the bleen model, but the way that light is distributed is very similar. That is basically what happens, right? So let me show you that on the demo again. And yeah, it turns out that the difference is almost unnoticeable. Okay, so this is, let me, in a second. So this will be bleen, and I will get this one. In a second, the other window is here on my other monitor. Okay. Okay, so this is bleen, and this will be Phong. So I will put, I don't know, the same numbers, 63 and 36. 63 and 36, right? So do you notice something different? So you can see like the amount of, yeah, like the scatter portion of the light in the case of Phong is just a bit bigger, right? So it goes a bit farther, and this one is just a little bit less, right? That's the only thing, right? So for example, here in the backlight is maybe more evident, right? This is a bit more scattered than this one, right? But it's fine, right? It's not a problem, right? So this is something that happens a lot in computer graphics, and it's also important for you. You don't always need to exactly mimic the reality and things like that. In computer graphics in general, if it looks good, perfect. Even if we are talking about like a super sophisticated research in I don't know, a SIGGRAPH paper or things like that. I mean, I'm already told you that contributing to science right now is way harder than like 20 years ago. But in general, that rule is still kind of valid, right? That in computer graphics, if it looks good, looks good. So there are a lot of very how do you say this? Smart algorithms sometimes that they're not exactly mimicking the reality. They're just like very cleverly hacking something that looks very similar to the reality. In computer graphics, that's perfectly fine, and it happens a lot in for example, in fluid simulation, explosions, things like that. I mean, exactly simulating a real explosion is incredibly complicated and very, very expensive, right? If you want to exactly do the same as physics, right? Okay, so basically we have this, right? Phong versus bleen. So as you can see, it's almost the same. It's just Blinn is a bit more cheaper, right? And we have another break. Any other question? Okay, Tommy has a question. When do we choose Phong versus Blinn? I think currently you probably always use Blinn because in the end it's cheaper, right? And again, because the difference between Blinn and Phong is almost nothing. I think everybody will say that you can use Blinn. And also remember, you can also play with your shininess, right? So basically, if you take a Blinn algorithm and just modify a little bit your shininess number, you will almost get the same result as Phong, right? Because shininess also deals with that, right? The shininess basically modifies the way your light is distributed, right? Okay, Canis, correct me if I'm wrong. The max difference is 45 degrees. What do you mean the max difference?
Oh, I mean it's like the angle between H and N and the difference angles between the H and N and V and R.
Here?
Yes.
Yes, you're right. Yeah, exactly. Okay, good. So now, obviously, what we are doing right here, it also depends on lights, right? On the type of light that you have in your scene, right? So usually we have three types of lights. I mean, there are more types of lights. There's another one called area lights. We'll also talk about that when we talk about ray tracing. But for now, you can imagine that there are only three directional lights, in which that basically they are just defined by direction, literally. This basically mimics the sun, right? So what happens is the sun is a source of light that, strictly speaking, is similar to a point light. A point is basically defined by location, which means that the light rays from a point light are basically coming from a single point and they're going out everywhere, right? That is exactly what happens with the sun. But the thing is, the sun is so far and so big that the actual rays from the sun are almost parallel, right? So a difference between a important difference between a point light and a directional light is that in the case of point lights, the shadows, right? In the case of point light, a shadow gets larger, right, when it's farther from the light, and you can experiment this in your house. So take, for example, I don't know, like turn on the light from your cell phone, and try to like, I don't know, to produce a shadow, for example, with the leg of a table, and you will see that the shadow obviously increases its size when it's farther from the light, right? And it makes sense. So imagine from here you have a ray that is coming in this direction, and from here you have another ray that is coming of this direction. Of course, the shadow will get like a conic effect, right? That it doesn't happen with the sun. So if you go outside and it's a sunny day and you see the shadow in a sunny day, the shadow of a very tall building, right? That shadow is not changing in size, right? It's basically the same because the rays from the sun are basically almost parallel because it's too far. And there's another type of light that are called spotlights that are basically similar to a point, where they're defined by location, direction, but also an angle. So this is basically similar to an office lamp, right? In which you have a piece of metal or plastic that is covering your spotlight and is basically restricting from where your light rays are coming, right? So you can see like this spotlight in theaters and things like that. Is very noticeable, right? So what happens here is, in your code, right? If you are like computing the light in your code, you are depending on the position of the light, right? So the thing is, the only thing that you need to change if in your code you want to mimic a directional light or a point light or a spotlight is just taking this into account, right? So if, for example, it's a directional light, right? What you need is only the direction of the light with respect to the world, right? So you don't need to literally compute different vectors, right? Depending on where is the light. So for example, give me a second. This is this is a point light, right? Because every time I was changing the position of this light, right, I need to recompute this vector right here, right? If I want to mimic, if I want to pretend that this is basically a, for example, the sun, and it's basically a directional light, what I could do is I could, for example, compute the, I don't know, maybe the vector between the light and the sphere. Let's pretend the vector between the light and the sphere. It will be like a vector like this. So basically, I won't recompute the light vector for every vertex, right? Because basically, I'm just using the same vector for everybody. Which means that instead of sending the position of the point in your vertex shader as a variant variable to the fragment shader, you could directly on your vertex shader define a global direction of the light, and or you can actually define it on your JavaScript and send it as a uniform variable, right? Which is global for everybody. And you say, okay, I have only one light and this is the direction. And once you are computing Phong or Blin or whatever you want to compute, you don't need to compute this vector right here, right? The vector light, you don't need to compute it. And you didn't need to interpolate that value from your fragment shader because it's basically the same for everybody, right? So the model that we were seeing, it was basically assuming that the light was a point. And in the case of spotlights, it's a bit more complicated because in that case, you do need to take into account the angle, right? But you also need to get a direction from the light also as a uniform variable, right? And basically you will need to compute the difference or the angle between the light direction and the actual direction from your spotlight to see if you are actually being lighted by the light or not, right? And I'm not going into like details of the formulas or the equations you need to solve this, because this is the one of the things that you will need to solve for your coding assignment, and I will not give you all the answers, right? I'm already showing you a lot of code. Okay. Questions about lights? Do you have any questions about lights? Yes, Nam.
Okay, I might have missed a part about how the angle of light is already predefined in the fragments. So when exactly is the information passed into the fragments?
Okay, let's see. Use with which type of light? Spotlight?
The L vector is basically pre-populated for every fragment, given that everything is static. Right?
Okay, but again, assuming that it's a point light, right?
Well, does it matter whether it's a point light or a directional light?
It is because so if it's a directional light, right? All the rays are parallel. It means that it doesn't. You don't need to compute the actual. You don't need to compute this vector, because now the vector that you will use is this. It will be the same vector for everyone, for every vertex and for every fragment. It will be the same. So you basically define the direction of your light as a uniform variable, and just send it everywhere, right? That will not be interpolated or anything, right? It will actually be cheaper, right? So computing, for example, rendering things, assuming that the light is the sun and it's a directional light, that is actually way cheaper. If it's not directional light, if it's a spotlight like this one, right? What you need to pass from the vertex shader to the fragment shader is the position of the light. Right.
The displacement between the
So you can send the position. You can actually send the position as a uniform variable, right? Because you also can get that on the vertex shader, and the vertex shader, and also on the fragment shader, right? So what you will do on the fragment shader, sorry, is you will basically need to compute the vector from that uniform variable, right? From that position from the light, minus your position, right? And you will get this vector. And obviously that will change for every fragment, right?
Right.
Okay, good. Okay, and you had another question. How is the foggy foggy flooded light effect simulated. I don't remember. Sorry, I don't understand your question. What do you mean by that?
Oh, the spotlight effect a few slides forward.
Oh, I see. I see. This. Sorry. This,
yeah, there seems to be some kind of mist floating in the
yes,
air
yes.
or something.
Yeah. I did that on purpose just for you to visualize the spot. But this is a very sophisticated effect. Yes, I mean you will not get this for free. Yeah, this is totally different. Yeah, good question, but yeah, this basically I simulated that cone for you to see the cone, but like simulating this fog effect, it is very complicated. Yeah, it is. I think right now it doesn't make any sense to talk too much about this. Yeah, basically this is called, actually the name is volumetric lights. You can Google a little bit of that, and again you will see you will get probably into tutorials or books or things like that talking about volumetric tutorials with respect to real-time rendering, or volumetric tutorials with respect to real-time rendering. We are talking here about real-time rendering. It is very challenging. You will probably need to literally create a mesh, right, like a cone, and simulate the cone, simulate like the color of your cone as being this volumetric light, right? But it will be a very challenging effect. You will probably work on that. Okay, good. So there are other types of models. So for example, there's another one called anisotropic shading, right? So if you have like brush metal stuff like this one, this is exactly the effect that you will obtain. This, and again, I will not give you a lot of detail because this is a part of your assignment. So what happens is what happens here is you need to assume that the microstructure from this surface is like made up of like tiny cylinders, right? So what happens is if I return to trees to the max here, let me see if I can change. Oh no, actually I think I can show it on the other demo. Give me a second. I think we have two plane sphere host. Oh no. Okay, no. I thought it had cylinders, but it doesn't have cylinders. We still have 18 people. I'm super happy. Okay, give me a second. Let me super quickly. So let me just quickly create a cylinder. Oh no. Give me a sec. Okay, so I will get different color for this guy, and I get this guy shining. Okay, so let's see how a cylinder behaves, right? How a surface behaves with this lighting, right? So if I have a sphere, with the same material, right? There's a difference in how the light is reflected in each surface, right? Here I can see like the shiny part of this of the render. The shiny part of the render is basically a circle, right? But here the shiny part of the render is basically a line, right? This is probably very obvious for you, but this is basically depending, or this is this is basically depending on the curvature of the object, right? So a sphere is an object that has curvature on basically the same curvature for any side, right? It has curvature everywhere, and it is a sphere. So of course the shiny part is obviously a circle. However, a cylinder has two different types of curvature. It has a positive curvature on the horizontal axis, right? But its curvature is actually horizontal. But in the vertical axis, the curvature is 0, right? So of course, in this direction, it will basically reflect way more light, right, in the vertical axis, because it has no curvature, and it's just basically everything is acting, is basically everything has exactly the same angle of reflection, right? However, on the other side, right, the effect is not the same, right? So what happens with certain types of materials, and this is, for example, this is specifically noticeable with hair, when you're like mimicking something with hair or brush metal and things like that, is that its microstructure is like something that is made out of a lot of cylinders, right? So depending on how are you seeing the surface, it will shine more light in one direction than from other direction. So if I return to this image here, imagine that each of these super tiny lines that you can see here is like a super tiny micro cylinder. Because basically what you do with brush metal, you take, for example, sandpaper, you make this thing turning, and you take sandpaper and you're like polishing or like scratching the surface of this metal, right? So by scratching this surface and turning the surface at the same time, you're like creating like micro canals, right, on this surface. So it is like this thing was made out of cylinders. So that's why you can see like more reflection in one side than the other. And basically the way you can fake that, because obviously you will not literally create micro cylinders on your mesh, right? That will be crazy. So what you do is basically you have another variable, which is basically like a tangent for your surface, and depending on that tangent or that vector, you can decide where this object is basically shining more or not. And so, for example, if I return to the demo, sorry, sorry, there's a phone call, but I cannot join the phone call right now. Okay, so I will assign the same material, but now I will modify the shader, and I will use the anisotropic shader, right? So now the anisotropic shader, I have a specular level, right? And I have glossiness also. But now I have an anisotropy value that it basically is defining if, as you can see this part of my screen, now the graph, now I have like two axes for the graph, right? So basically one axis will represent one direction of the curvature, the other axis will represent another direction of the curvature. So if I increase this value, what I'm getting, or what I'm forcing this object is, you can see it here actually. You can see the difference, right? This is not having an anisotropic shader, right? Basically you have curvature on every side. But if you do this, you have less curvature in this direction. So basically your light is being concentrated in only one side, right? So you get this type of effects. And it's very cool. And it's very interesting to implement that. And you will also need to, to implement that on your next assignment, right? Okay, and then is another family of rendering techniques are called non-photorealistic rendering, and this I will very quickly pass these things. So one, for example, is called toon shading, right, or cell shading, right? And instead of trying to mimic like a super realistic material, you basically create like borders and a quantized shading colors for your object, and you can get things like this. This is actually used a lot in modern days for certain cartoons. So for example, The Simpsons or yeah, like very old school cartoons like that. Basically everything was animated in 2D animation software, right? But then when 3D animation was a bit more easy to get, it started to become very very common to for example, I think the first, let me try to remember, this character Fry is, whatever. There's a cartoon that is actually created by the same, I think it's created by the same creators from The Simpsons. I don't remember right now the name, but basically that was the first. Yeah, Futurama. Thank you so much. Yeah. So for example, Futurama is also very old, but Futurama was the first TV series or TV cartoon that started to have 3D environments rendered as toon using toon shader. Those guys were the first in using that. I was there at that time. I remember that when I start to see like the first chapters from Futurama, I was like, oh my god, what is this? Because we didn't know that it was 3D. We thought it was drawn in 2D, but suddenly the perspective was impressively realistic and everything was amazing. Well, it turns out that they had this idea of combining 2D and 3D. So in many scenes from Futurama, what you're seeing is it's basically a hybrid animation. You have a 2D animation from the characters, and also a couple of props there, but sometimes the sheep or certain environments, those are actually 3D models, but rendered in such a way that they seem like a 2D. And this is basically called toon shading, and that was the first series that basically do that. There's another type of shader called Gouraud shader. This also is also very, very, very old. This is from 1998, 1 year before I started to work on the computer graphics. And this basically what it does is, depending only on the direction of the light, it doesn't compute anything. You don't need to compute any dot vectors or things like that. So this one is also super, super cheap, and it was very good at that time. What you only do is basically the areas that are on the direction of the light, you will assign a warm value, right? A warm color, and the areas that are on the other side of the on the other side of the light, you will assign a cool color, right? So this is basically the effect that you get. And they usually also add contours similar to toon shading, right? So this is called Gouraud. And here are a couple of formulas that this is just a hint for your assignment. And finally, the last thing that I wanted to talk about, and oh my god, we have 1 hour and 35 minutes, is that you can also do a lot of experiments with shaders. Shaders is a part of computer graphics in which there's a lot of freedom. Again, you don't need to necessarily simulate exactly the physics of something. So let me tell you something. This happened to me a couple of years ago. I think it was in 2016. We were working on a project, and one of my colleagues from my department, he was working on a paper in which they needed to simulate fabric. But the thing is, they needed to show in real time fabric with wrinkles, right? But they didn't want to have lightning and shadows because they wanted the people to perceive the wrinkles without any like shadow affecting the wrinkles, right? So it was like, oh, okay, it's kind of hard, right? Because you need light to shine into objects, right? But somehow you need light but not shadows, and yeah, it was kind of confusing. So in the end, what we needed to do is to kind of like mimic what you can see in velvet fabric, right? So what happens with velvet is that the microstructure of velvet, right, is that this fabric has like a very, very tiny layer of small hairs, right? And these small hairs from the fabric, basically they reflect light, right? So what happens with this type of material is that they shine, right, kind of in the edges of the mesh, in which basically the normal of the surface, right, is perpendicular to your side of view, right? So I needed to come up with a very quick solution to this, right, to a shader that could work fast and be like good enough. So I will show you what I did. Where's demo? Okay. So this is basically the 3D model. Obviously, is just pink because I haven't shown you exactly the solution, right? And we have, give me a second. And we have, so this is basically the fragment shader, right? So the JavaScript is very similar to the templates that we have used. This is very, very similar. It's just creating the uniform variables, blah, blah, blah. The vertex shader is super simple. I'm just getting the normals, right, in view coordinate system. I am getting the normals multiplied by the normal matrix. I'm getting the view position. This is important, right, the position of the camera. This is very simple, right? And in the end, here, I didn't need specular level, right? Because we didn't want to show shininess with respect to a light. Actually, we didn't have any light, right? So we wanted only to mimic velvet without any light, without any shadows, without anything, right? Just hacky version, right? So my idea was, okay, I probably need only to have just ambient color and the fabric color, obviously, right? The color of the fabric and only ambient color. And ambient color is just, again, remember the ambient is this fake effect that lights comes from everywhere. So this is how it would look a material that is red and that it has just is lighted by light that is coming from everywhere and it doesn't have shadows, right? This is basically how it looks, right? There are no shadows and light is coming from everywhere, so this just looks flat, right? So the goal here was to, again, mimic the velvet effect. And the velvet, again, as I said, is shining on the edges of the surface, right? Of the part of the surface that is basically, its normal is perpendicular to your side view, right? So what I did is this. I will copy my code. I will copy, and this is, right? So this is what I did. I created this variable that is basically getting the dot product between the normal vector and the view vector, right? This is, I have the direction, the view vector is the direction from which I am seeing the mesh. And the normal vector is, of course, the normal from the fragment, right? This is already an interpolated normal, right? So I take the dot product, right? And if the normal direction is basically at 90 degrees from my view, that product will be 0, right? So I was getting 1 minus that, right? Because I was exactly the opposite, right? I wanted to get 1 if the normal of the surface is orthogonal to my view, right? Because that is like that part of the surface that I want to shine more, right? Then I just get the max value between that value and 0, is this part, right? Then I multiply that value times the light color, because I didn't know if they wanted to change the color of the light. So I said, okay, maybe they want to change the color of the light. So I just multiplied that by that. And I made this very hacky thing, right? I'm not actually adding these components. I'm just taking the fabric color and I'm multiplying that times the ambient plus the fabric. And it's actually, it looks very weird. But this is the result. So as you can see, is very decent, right? So there are no lights, there are no shadows or anything, right? And you could see the structure, you could see the wrinkles, right? And you don't need to compute too much, right? So as you can see, what is happening here is basically the shiny part of the surface is the one that is, again, the one that its normal is orthogonal to our view, right? If the part of the surface is basically looking at us, if the normal is looking at us, right, it's just darker, right? So yeah, you can do things like this that look very, very nice with just a couple of lines of code, right? And still, this very hacky solution that it was, I had to do this like in a very, very short amount of time, a couple of minutes. It has a couple of problems. This is actually not as orthodox, or it's not exactly correct. So I want for you to take a moment to think about it, and because I will ask you to actually create another velvet effect for your, you will need to create a lot of shaders for your next assignment. So one of those shaders will be a velvet shader, But I don't want for you to basically copy mine, right? I want you to think on how can you, for example, modify a Phong shader, which has all these other components that are important, right? The diffuse color, the ambient color, and everything. And how can you basically modify that to act as a Phong shader? But because what happened here, for example, is that I don't have too much control on how much this shininess is basically behaving, right? The good thing about the other model, in which we have, for example, the shininess is in the specular value using Phong, is that I am also multiplying that value times this glussiness exponent or shininess exponent, and I can play with that to get different results. And I don't have that, right? So, for example, maybe a more orthodox way to solve this will be maybe like basing everything in a Phong model, and maybe modify the specular level to act as this like velvet effect, okay? But okay, I will stop talking because otherwise I will give you the solution. So thank you so much. Thank you for being here, and I will upload this video and see you on Monday. And also I also uploaded the theory 3 assignment. So please check that out, okay? See you everybody.